Alright, ladies and gentlemen, we're looking at 9.1, day 2. We're talking about series now. Okay, now we're going to represent the series using sigma notation and find their sums. Okay, now, the important difference we're going to have to get into here, a series, unlike a sequence, is a sum of a sequence. Okay, so if a sequence is basically a list of numbers, so 2, 5, 8, 11. As soon as I say series, again, it probably doesn't sound very big difference, but I mean 2 plus 5 plus 8 plus 11 as soon as I say that. And of course, then we can add those up when we want to. But anyway, that's the difference. As soon as I say sequence, I just mean a list. When I say series, I mean we're going to add them all up. Important distinction. Try to keep that straight. Alright, for this lesson, I know we got done using imaginary numbers recently, but we're going to use it as a regular variable now. Alright, now get a sigma or summation notation. Okay, the sigma symbol is this Greek letter right here. It's kind of the Greek version of the letter S, hence sigma. And we use in mathematics that for sum. I've got this over here now. In a lot of movies like Good Will Hunting, and a lot of movies where some super smart guy writes stuff a lot, they use that symbol a lot. And here's our sigma symbol, and he's got a little infinity on top, it's hard to see, and a little n equals 0 on the bottom, and we're going to do stuff just like that here in this lesson. Alright, but here we go. Sigma notation is just a method for showing a series in a more compact way. So again, this is actually just representing a series, so a sum of various things. Okay, so basically what this means, and it's not real obvious right now because it's the first time you're seeing it, but okay, it says k equals 1, and it gives me this k squared, and it gives me the 5 up here. What this actually means is I'm going to basically plug this value into the expression out front here, so putting a 1 in there just gives me 1 squared, obviously. And then I'm going to sum everything up until this number here. So I plugged in 1, I'm going to plug in 2, etc. Plug in 3, plug in 4, and then finally I reach my top number, 5, and so that's my last one. So again, Matt Damon here writing some fancy thing, that's all he was representing. Hey, I'm going to add up a whole bunch of stuff. Granted, using an infinity on top means he's going to add up an awful lot of stuff, but that's what the basic idea is. Okay, but that's what that means, but let's get a little more detail and then start using this in a more meaningful way. Alright, we're nothing really to write on this slide, but in general, here's basically what this whole thing means. Okay, again, the book likes to use I a lot, so I'll use I just so that when you see it in the book you don't freak out. Okay, so this right here is just going to be the variable we're going to use, and then we're going to start with some number here. This m is actually going to be a number. Likewise, this n up here is going to be a number. So you'll see numbers there and there. And then this a sub I is just whatever expression. The last one I used a k squared, and this one it would have been an I squared since I'm using the letter I. Alright, so that's where things are going to go. I know this might not make a lot of sense now, but as soon as we start doing a couple examples, hopefully it'll make a lot more. Alrighty, so here we go. I've got I equals 0 to 8, basically. So again, I'm going from 0 to 8, and using the expression 2i minus 1. So as it says here, basically what we're going to do is plug I equals 0 to 2i minus 1. So hopefully I can do this without showing the work, but if I plug in a 0, 2 times 0 is 0 minus 1, that's just going to be a negative 1. And then again, I'm dealing with a sigma, so now I'm going to be adding to it, and then I plug in my I equals 1. Plugging in a 1 here gives me a 1. And then again, I'm still doing a sigma, so I'm still adding up for this series. And then I plug in I equals 2. 2 times 2 is 4, minus 1 gives me a 3. And if you maybe notice a pattern, we can keep adding in. Next one will be 5, and then I keep adding in all the way until I plug in the 8. 16 minus 1 is 15. Now granted, I got lazy here and didn't write them all out, so what I need you to realize is find the sum of those, how many values. Well, if I'm going 0 to 8, a lot of people say, oh, that's just 8. Well, again, 0 is the first one, then 1 is the second term we get, ultimately meaning that once we get to 8, we've actually got 9 different values to add up. That may not seem like a big deal now, but later on that's going to come into play and be very, very important. Alright, and there are certain properties you can use with this sigma notation. C is going to be a constant for what we're talking about here. But okay, if I've got this, and notice I've got C as a constant, so I've just got a number out in front. So I've got from 1 to n. Well, basically all that happens here is you're going to take that C, and then as I keep plugging different variables, if it's a constant, there's nothing to plug into, so basically that C won't change. So if I go from 1 to n, that means I have n C's all lined up, so basically that's simply n times C. So fairly unexciting, but if you're doing a summation of a constant, it's just however many terms you have times whatever that constant is. Okay, so there's property number 1. Alright, now remember, a sub I is going to be an expression of some sort, but for property number 2 here, if I've got, again, some constant in front of that, so kind of a common factor that's been factored out. Can you imagine plugging that 1 repeatedly and then multiplying each one individually by c? Well, if you wanted to, you could kind of like factor the c out of the whole thing, and then you get your nice little sigma I equals 1 to n of whatever that expression a sub I was. So any constant you can factor in front of the whole thing, so just do the summation of the simpler expression, take the result times c, if you want to. And then maybe this one won't come as too much of a shock here, but if I've got this expression out front, which I can think of as a sum or difference of two separate expressions, all I really need to do, if, again, I would like to do this, I'll confess it's not really necessary frequently, but, you know, it's kind of nice to have in your bag of tricks to use if you need it. And you do the sum of the first guy, and then plus or minus. Again, if I used a plus here, I'd use a plus here, minus, minus. And then you can do basically the sum of the second thing. So I just want n of the b sub I, and then get those two sums and add them together instead of doing each piece within each 1 through n, whichever step you're on. You could do it as two separate chunks if you wanted to. I confess again, these are here mostly just for the sake of argument. I don't use them a whole lot myself, and honestly I don't expect you guys to very much either, but there it is. Okay, so let's put this to use. Again, I'm doing a summation of 1 to 4 of the expression 2i plus 3, again, using that I as a variable and not as the square root of negative 1. Okay, so again, using those properties, we could break this up into a few different chunks. For instance, I could do the summation of 2i from 1 to 4, and then the summation of 3 from 1 to 4, and then if I wanted to, I could actually factor out the 2. I'll be honest, without really directions to do so, I probably won't mess with that, because again, basically all I have to do is plug in 1, plug in 2, plug in 3, plug in 4, and add it all up. So basically plugging in the 1 gives me 2 times 1 plus 3. I couldn't write that sloppier if I wanted to. And then plus 2 times 2 plus 3. Then 2 times 3 plus 3. And then finally add on the 2 times 4 plus 3. Okay, now depending on the messiness of this expression, it may or may not be a good idea to use parentheses around these things, so just for argument's sake, I'll throw the parentheses in there, but I confess in this case it really wouldn't have mattered one way or the other. But again, messy expressions, especially when you start having negatives and things floating around, sometimes holding things together with parentheses really helps make easier to avoid mistakes. So anyway, adding this up, I'd get a 5 right there. Next piece, I get 4 plus 3. I'm pretty sure that's a 7. 6 plus 3 is 9, and then if you notice the pattern, I don't really have to do the work here, but that's going to be an 11. And then, well, I'm going to cheat here and go 5 plus 11 is 16, 7 plus 9 is also 16, and now 16 times 2 is 32. Ooh, so basically this is a very fancy way to write 32. Alright, well, if we can use the notation one way, we should be able to go reverse. So if I want to rewrite a series into sigma notation, okay, now one thing, as it says here, there is more than one way to write these things usually, and the book likes to use I for its variable and start with I equals 1. I mean, there's no rule that says you have to start with 1 each time, and quite honestly, depending on the numbers, sometimes it's easier not to start with 1. For example, this one, if I just have 1/2 plus 1/3, etc., all the way up to 1/9, well, what the book is going to want to do, it's going to look at this thing and say, okay, well, sigma, and it's going to say I equals 1, and start doing stuff before it even thinks about anything else. Okay, well, what's nice here is the numerator is always a 1, so my expression out in front is going to be 1 over something. And that something, well, 2, 3, 4, that's pretty simple. Again, starting with 1, I've got to have a 1 down here, but I really need to get it up to a 2, so by adding 1 onto it, I get the 2, and then again, by plugging in subsequent values for I would generate the 3, 4, etc. Getting all the way up to 9, well, if I put an 8 here for I, plus the 1 gives me the 9, so that tells me that I'm going to have to stop at 8. So there would be my expression that the book would give me, but quite honestly, I think that's messier than what you have to do. So what Mr. O might do is throw down my sigma, and again, I'll keep with the I just for argument's sake, but I could use any letter I really wanted to there. But here we go. Okay, now again, I have a 1 over, which is a pretty standard, well, I think it'd be silly to try to do something other than put a 1 up there. But now here I'm going from 2, 3, 4. Well, why not just throw an I down there, start with 2, and then go all the way up to 9? Okay, now these two expressions would generate the exact same list of numbers and the exact same sum. It's just, quite honestly, I think mine's a little easier to plug into because I don't have that extra little +1 floating around. But whatever works. The book is going to give us the one on the left, but honestly the one on the right does the exact same job. Okay, another example. Now here it looks very messy, but and the book is going to do this too, that's why I'm doing it now. The book is nice enough to kind of chunk things together here. So basically, a little hint, this is the expression you want to kind of generate in front of the, or actually behind the sigma sign, and then try to do something that fits the pattern. Alright, so anyway, again, I'll throw down my sigma sign, and again, because I'm the book now, I'll say I equals 1. Although looking at the pattern, I've got a 1 to start with, and I go to a 2, and then maybe it's not overly obvious, but I go to a 13. Basically, I'm just counting up by 1 on top of this fraction. If you notice, everything else, though, is completely the same. So basically, all I have to do is throw down my big old bracket here. Okay, again, it's always a 5, so I'll just put a 5 there. Plus, and I've always got this parentheses here. I've got a 2 on the bottom every time. And what I've got on top is this, well, I'm going to count from 1 to whatever, so I'll just throw the I up there for now. And then it's always cubed, so that makes it easier, and then that's the end of the thing. So I got this, and quite honestly, if I'm just going 1, 2, etc. to 13, kind of makes it pretty easy. That's got to be a 13 up on top. Okay, again, we could probably fancy this up if we want, but there you go. Okay, another thing that's going to happen from time to time is sometimes, if you're writing out something like this, not simplifying is a really nice thing to do to help your reader. So I could have turned this into a 1, but then it would make it look a lot more confusing, I think. So sometimes it's nice not to simplify things on occasion when you're trying to get your message across. Alrighty, now I just made that comment about not simplifying sometimes. That does not apply to final answers. All final answers need to be simplified. Don't try to throw that one back at me in the future. Alright, anyway. Okay, so I've got this series here, which is a combination of fractions and non-fractions. So first thing I'm going to do when I ever have that is I'm going to turn everybody who's not a fraction into a fraction. Okay, another few things to take note of is it goes from positive and negative back and forth. And then I've got basically 2 separate sequences of numbers going in the top and bottom that help make up the series that I have. Alright, so anyway, that being said, going to my signal notation, starting with I equals 1, make that look like more like an equal sign. Alright, well, one thing that's going to be nice about this problem, relatively easy, is I can just look and simply count, and I have 1, 2, 3, 4, 5, 6 different terms. So I know my I value is going to go from 1 to 6. Okay, now the more difficult thing is going to be figure out the expressions that'll give me what I'm looking for. Okay, well, first thing first, I've got positive versus negative flipping back and forth. So that lets me know that we're having -1 to a power going on. So I'll just put the I up there first. But remember, if I start with a 1, this is going to give me a -1 here, and I want a positive to start with. So basically, what I need to either do is put a plus or a -1 on the I here to change the exponent to an even number to start with. And I'm an optimistic, happy kind of guy, so I'm going to use a +1. But -1 would generate the exact same result, so you choose whichever one you like better. Okay, my numerator is not so bad. 1, 3, 5, 7, 9. I'm simply counting up by 2's. Okay, and without going through a big long explanation of this, hopefully you can believe me when I say it's simply 2n minus 1, and I didn't mean to write an n, I wanted to write an I, so just pretend that that's what I did. There's an I minus 1. Okay, the denominator is a little funnier, 1, 2, 6, 24. That may not be a sequence that you recognize quite yet, but if you remember, and I get really excited about the number 1, it's really just equal to 1. If I then get really excited about the number 2, it's a 2. And then I get really excited about the number 3, all of a sudden it's a 6. And then I get really excited about the number 4, it's a 24. Okay, I'm kind of playing around there, obviously. Remember, that means factorial. 1 factorial is 1, 2 factorial is 2, and again, that just means times itself, and then times everything else down to 1. So 3 times 2 times 1 is 6, 4 times 3 times 2 times 1 is 24, etc. If I work at the 5 factorial, and 6 factorial, I will in fact get the 120 and the 720. So basically that's what's happening in the denominator. I'm taking my I value and going factorial. Alright, so granted, kind of needed 3 pieces to put this guy together, but that's what this guy would be in sigma notation. Alrighty, this last example is really just to kind of give a little vocabulary term the book's going to throw at you and hopefully not have you freak out. Okay, it's going to say find a partial sum or something like that at some point. Well, it's a fancy way of saying find the sum of the first n terms. Okay, and if that didn't work for you, if I say find the fourth partial sum of this, now notice it goes from 1 to infinity, so, well, okay, so basically we're using the partial as not the whole thing, and the fourth one, meaning basically you do the first, second, third, and fourth all together. So when I say find the fourth partial sum, basically just means find the sum of the first four. Okay, so I'm not going to work this thing all the way out, but basically all we would do here is the sigma I equals 1, we would just take it up to a 4 basically, of 1/3 to the I. Alright, so again, plugging in a 1 would give me a 1/3, plugging in a 2 would give me 1/9. I'm just taking this as an exponent. Then I get 1/27th, and then the fourth one would be 1/81, and then we would simply add all those up. If you're interested, that works out to be 40/81, but whatever the case, there it is again. Don't let the infinity freak you out, especially when I'm saying the fourth partial sum. Just kind of imagine that infinity being whatever number that you're supposed to be going for, and just work it out like the other ones we've done. Alrighty, hopefully that made some sense. Of course, as always, I'll see you in class.